Hello and welcome to this second video for week 14. The previous video, part 1, we talked about fatty acids, which are one type of lipid. In this video, we will be talking about triacylglycerols, which is a second category of lipid. Triacylglycerols, I will start by letting you know that triacylglycerols go by several names. Triacylglycerol is the same thing as a triglyceride. That's what a medical professional often will use. And a very common term would just be fat. If you talk about fat in your food or fat on your body, you're talking about this larger molecule, triacylglycerol or triglyceride. That's not the same as a fatty acid. So I want to make sure that we have that understanding to start. We learned about fatty acids in the previous video. Fatty acids are smaller. Fatty acids are bigger. Fatty acids, I'll write this out also. Well, I won't. Yeah, I will. Fatty acids are used to build fats. If that larger molecule happens to be a liquid, a lower melting point and therefore liquid, it's usually referred to as an oil. Fats and oils. Fats are solid. Oils are liquid. Otherwise, they are the same thing. They are the larger or bigger molecule, more formally called a triacylglycerol or a triglyceride. What we'll do in this video then is to learn how to draw and identify structures of these triacylglycerols, and then look at two reactions, how those triacylglycerols are formed, and then how those triacylglycerols undergo hydrolysis. We'll start with this first one, structures of triacylglycerol. This is a structure of triacylglycerol. I will say this to start. Notice that structure down there is not a fatty acid. It's not a fatty acid. A fatty acid, as you know, a fatty acid is a single hydrocarbon chain with the carboxylic acid group. A fatty acid is a single hydrocarbon chain with a fatty acid group at the end of it. We saw that in video 1. This structure, as you see, has 3 chains, bottom, middle, top, not just a single chain, and there's not a carboxylic acid group anywhere. In fact, instead of the carboxylic acid functional group, what you see here, a carboxylic ester group. This is carboxylic ester. And in fact, you will see 3 of those functional groups. 3 ester groups. So if you are using the structure to identify a triacylglycerol, this is what you'll notice. There will be 3 ester groups, 3 long hydrocarbon chains, and this, what I'll call a backbone of 1, 2, 3 carbons. So 3 carbons, each has an ester group with a long hydrocarbon chain. Ester, long hydrocarbon chain, and so on. This is a triacylglycerol. So looking at structures of triacylglycerols, they are, I can summarize what we just said, they are larger than fatty acids. They have a 3-carbon backbone with 3 ester bonds and 3 hydrocarbon chains. You learned about ester bonds when we learned about making esters. And this is an ester functional group, but it is also an ester bond. And we'll be seeing that in more detail when we look at these reactions. So the structures of triacylglycerol, this is the feature that you're looking for. How can you tell the difference in structure between a fat and a fatty acid, triacylglycerol and fatty acid? Remember, these three names are interchangeable. Triacylglycerol, triglyceride, and fat. Those three names are interchangeable, but not this. Fatty acid is its own thing. It's a smaller molecule consisting of a single chain with a carboxylic acid group. The larger molecule has a 3-carbon backbone, 1, 2, 3, with 3 ester bonds, 1, 2, 3, and 3 hydrocarbon chains, 1, 2, 3. I will have you notice that the 3 hydrocarbon chains usually are not all 3 the same. That would be pretty unusual. Usually the 3 hydrocarbon chains are not all 3 the same as each other, and here they're not, right? This chain is a saturated chain. The middle chain is monounsaturated. The bottom chain is polyunsaturated. It's typical that the 3 chains are not all the same. So what we've just done is looked at structures of triacylglycerols. I would like us to start focusing on reactions. That'll also help us understand these structures a little bit better. So I'm going to say that we have drawn the structures of triacylglycerols. I'll check that off, but we'll revisit it as we're looking at these two reactions. So please join me on page 189, which is our next page, looking at the reactions of lipids. It's going to be a condensation reaction. You've seen this reaction before. When 2 monosaccharides combine to make a disaccharide, for example, that's a condensation. We have been saying that the CO indicates something is going to combine. And specifically, what's going to combine here is that 1 glycerol will combine. 1 glycerol combines with 3 fatty acids to form, this is a formation reaction, to form a triacylglycerol. So we are starting to talk about the reaction that will form a triacylglycerol. The reactants will be a glycerol molecule and 3 fatty acid molecules. The structure here is not one that we've seen before. I'm calling it a block diagram. Notice that there's no bonds or carbons or oxygens or anything. It's more of kind of a schematic structure of what the triacylglycerol molecule will look like. But I'm going to, for the moment, pull up the page we were just working with to show you how it relates. This triacylglycerol molecule here that's shown in detail is what I'm indicating by this block diagram. This block diagram is a triacylglycerol, just like this detailed structure is a triacylglycerol. This 3-carbon backbone came from a molecule called glycerol. We call this a glycerol backbone, and there are 3 fatty acids attached, 3 fatty acids attached. So these 3 chains that you see here came from fatty acids, and the 3-carbon backbone came from glycerol. So this is just kind of a schematic or summary way to show that. We'll see it in more detail, which I think will help, I hope, help make it make a little bit more sense. So here is that schematic. 1 glycerol combines with 3 fatty acids. You have not yet learned what glycerol is. We're seeing that right now, but the OL ending should indicate to you that that must be an alcohol. Sure enough, here it is. This is glycerol. It's not a category. This is a specific molecule. It's not a category of molecules. It's its own molecule, just like water or oxygen or carbon dioxide or ammonia or sugar. I mean, not even sugar, a specific like NaCl, sodium chloride. This is a specific molecule. It has alcohol, not surprising because OL ending indicates that. There are 3 carbons and each carbon has an OH group. So you should know how to name this molecule as glycerol, and you should know how to draw this name as that structure. That is the name for that structure. I think the way that you can remind yourself that there are 3 carbons is because glycerol is what's used to form a triacylglycerol. Tri, of course, indicates 3. So 3 carbons, they each have OH. That's one of the ingredients, a glycerol, plus 3 fatty acids. Here's the first fatty acid, here's the second fatty acid, here's the third fatty acid. Notice that this particular example is abbreviating the long hydrocarbon chain. This is abbreviation for the long hydrocarbon chain. So is this, and so is this. So it's just abbreviating kind of the rest of that fatty acid. What I would like you to notice is this. It's what you've seen before. When you are combining, remember, CO condensation reminds you CO, combine. Combining, condensation always has meant and always will mean box out water. We've drawn it to show the 2 functional groups pointing at each other. So we are going to box out water, H and OH. Just as before, it won't matter if you choose this OH with an H from here, or if you choose this OH with an H from here. That won't matter. The only thing you need to be sure to do is to box out one OH with one H. Don't box out an OH with another OH. That doesn't give you water. You want 2 H's and 1 O. And I notice that I have a chance to box out another H and OH and another H and OH. There's 3 opportunities to box out water, and that's why in this example of reaction, you'll get 3 waters as a product. Water 1, water 2, water 3. What happens to the broken bonds that happened when you boxed out water? You broke a bond right there, and right there, right there, right there, and right there. Those 2 pieces slide together, just like the condensation reactions you've been practicing. CH2 is bonded to an O. H is gone, O is gone. So now this O will be bonded to this C. And there it is right there. O is bonded to that C. This becomes the new bond. There's 3 new bonds because we boxed out 3 waters. These are the new ester bonds. 3 new ester bonds. And what we produced was triacylglycerol. So a glycerol plus 3 fatty acids, box out water, slide the pieces together, produce triacylglycerol, otherwise known as a triglyceride, otherwise known as a fat or oil. Please be very sure not to mix up these terms. Fat is not the same as fatty acid. Fatty acid is the smaller molecule, the fat is the bigger molecule. This is a good time for me to point out, I'll just put it here. Note, fatty acids generally do not I'll just say show up in your diet by themselves. Instead, your diet contains the larger fat triacylglycerol molecules. So it's very unusual that you would be eating fatty acids directly. You eat the larger fat molecule directly. So this is a condensation reaction to form triacylglycerols. This is how triacylglycerols are formed. Below this is a second example, a more specific example. I see that the printing is not that good. Here is glycerol. There's only one glycerol. It's a specific molecule. So every single triacylglycerol always, always, always starts with glycerol for sure. One of the reactants always is glycerol. The other reactants always are 3 fatty acids, but which 3 fatty acids can vary. We just saw in the earlier video, there's a dozen or so fatty acids that we encounter in our diet, in our bodies. Any 3 of those dozen could be used to make a new triacylglycerol. If you end up using 3 fatty acids that have lower melting points, then your triacylglycerol will have a lower melting point and be more likely to be an oil. If the reaction uses 3 fatty acids with higher melting points, then your product triacylglycerol will also have a higher melting point and therefore be more likely to be a fat. That's how you end up sometimes with butter and sometimes with olive oil, solid or liquid. It depends on which fatty acids are used. So this shows a specific reaction. Again, box out water 3 times and end up with 3 waters. When you slide the pieces together in a condensation reaction, here are your 3 new ester bonds. And the result is a triacylglycerol, otherwise called a triglyceride, otherwise called a fat/oil. This is the reaction that shows how triacylglycerols are formed. We said we also want to learn how our triacylglycerols hydrolyzed. How do they undergo hydrolysis? I think you won't be surprised to hear that this reaction is reversible. In fact, I can draw the arrow right now. It can go in reverse. In the forward direction that we've just been doing, that was condensation, how you form a triacylglycerol. But if we go in reverse, if we start with the triacylglycerol and pull it apart, that's hydrolysis. We'll see that separately on the back page, but I'd like you to notice it in comparison to condensation. It's just the reverse of what we've seen a moment ago. Hydrolysis and condensation are the reverse of each other. Let's flip the paper over though to see that specifically. Reactions of lipids, hydrolysis. Hydrolysis is how triacylglycerols what should we say, are hydrolyzed. To go back to fatty acids. I'll say it that way. And the little hint / trick / silly little thing that we have been saying is this: when you see the SIS part of hydrolysis, let yourself think of scissors, which means to cut apart. Scissors, that's what they do, they cut apart. And so sure enough, that's what hydrolysis does. It's like scissors, it cuts apart. It doesn't combine, that's condensation. Hydrolysis is like scissors, it cuts it apart. And specifically what it will cut apart, in general, it's taking something bigger and getting smaller. That's what scissors do. In the specific case of lipids, it will take the bigger triacylglycerol. Triacylglycerols are bigger, and it will do hydrolysis to get to glycerol and 3 fatty acids. Fatty acids are smaller, triacylglycerols are bigger. The ester bond will break. That's what we've seen in other examples. We have 3 ester bonds that can break. I'll write that 3 ester bonds break. And when those ester bonds break, one of the products will be the glycerol, the 3-carbon backbone glycerol. That will always be one of the products of lipid hydrolysis. The other product will be the 3 separate fatty acids. So it's just the reverse of what we saw with condensation. What's going on here? Why do we have 3 waters written there? Water was a product of condensation, which means water is a reactant for hydrolysis. Lipase is like a catalyst. Lipase actually is an enzyme in your body, but it's functioning as a catalyst, and you know what that means. It's something that's there to speed up the reaction. So this is hydrolysis, which is the reverse of condensation. Here it's showing a more specific example. It's showing the ester bonds that break. The 3 bonds drawn in red, okay, we'll draw them in red. The 3 bonds drawn in red are broken in hydrolysis, and I'll remind you, those are not just random bonds, those are ester bonds. Those are what get broken. And so when you break that bond, carbon, 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 this is what will form glycerol right here. And those 3 become the three fatty acids that get produced. So what we've just done in this video, we predicted products and draw the structures for formation of triacyl glycerols. That was a condensation reaction. The reverse of that was the hydrolysis reaction. Condensation and hydrolysis are the reverse of each other. If you are looking for more examples or additional explanation, I do have additional videos on this topic, and I invite you to take a look at those as you need to. Thank you for joining us.